Hi! In this video, we are going to discuss order properties of R. First, we will define what we mean by positive numbers, and then we will define the order relation in the set of real numbers. After that, are going to exhibit and prove important properties of the set of real numbers derived from the order relation. So if you're ready, let's start. So we begin by the definition of the set of positive numbers. There is a non-empty subset P of the set of real numbers, which we will denote by the blackboard letter P. And this is called the set of positive numbers satisfying the following. If we have two positive numbers A and B, then the sum is also positive. If we have two positive numbers A and B, then the product is also positive. So this means that our set P is closed under the operation addition and the operation multiplication. Meaning, if we add two positive number, the result is positive. And if we multiply two positive number, the result is also positive. Now, the third property of this set is that for any real number A, only one of the following holds. Either A is positive, or A is 0, or if that is not true, then negative A is the one which is positive. So for example, if we take the real number 2, 2 is positive. It is not 0, it is not negative. So if the number is not positive, and it is not 0, then its negative or its additive inverse must be the one which is positive. So that's what this set is saying. So you have three properties of this set. It is closed under addition, it is closed under multiplication, and it follows the trichotomy property. For any real number, only one holds. Either A is positive, A is 0, or the negative of A is the one which is positive. Observe that if we collect all real number such that the negative of A is positive, and we call that set the negative of P, then the set of real number can be partitioned into three disjoint sets. The set of positive numbers P, the set containing 0, and the set of negative numbers negative P. Again, these are partition, meaning they are pairwise disjoint, and if you get the union, you get the whole set of real numbers. So, we were able to divide the set of real numbers into three. The set containing just the 0 element, and then the set containing all positive numbers, and the set containing numbers whose additive inverse is positive. So those numbers we will call negative numbers. Having this definition of the positive numbers, we can now have an order relation in the set of real numbers. So how do we define an order relation? So let A and B be real numbers. If B minus A is positive, so for example, you have two numbers, B and A, and then you get the difference, B minus A, and then what you end up is a number which is positive. Then we can write that relationship as follow. We can write A is less than B, denoted by this symbol, or we can write B is greater than A, which is denoted by this symbol. So meaning, A is less than B if and only if B is greater than A. And that happens if B minus A is positive. So again, if you get the difference B minus A and the result is positive, so that means A is less than B, or B is greater than A. Now on the other hand, if the result is either positive or 0, then we write that relationship as follow. We write A is less than or equal to B, and we denote that by the less than symbol with a half equal symbol below. So that means it's either less than or it's equal. So A is less than or equal to B. Or similarly, we can write it as B greater than or equal to A. So kung saan nakaharap, kung saan naka-open yung inequality symbol, so these are our inequality symbol, yun yung mas malaki. Tapos kung saan nakaturo yung pointed side niya, yun yung mas maliit. So it's pointing towards the smaller value. These inequalities are called order relations in R. So we have 4 inequalities: less than, greater than, less than or equal, and greater than or equal, called the order relation in R. So again, this order relation is defined using the set of positive numbers. So you need to get the difference of the two real numbers and then decide whether it's less than, it's greater than, it's less than or equal, or greater than or equal. Okay, we have the following remark. For every real numbers A and B, only one is true. By the trichotomy property, if you get the difference A minus B, then you have the three possibility. Either A minus B is positive, or A minus B is 0, or A minus B is not positive, meaning the negative of that is positive. So that's the trichotomy property. To translate that into our order relation, so meaning for any real number AB, only one of this must be true. So if A minus B is positive, so A must be greater than B. On the other hand, if A minus B is not positive, which is the third case, so that means B minus A must be positive. So if B minus A must be positive, then that means A is less than B. Or if A minus B is 0, then that means A is equal to B. So this is another version of the trichotomy property given two real numbers. So if you have two real numbers, then either A is less than B, A is equal to B, or A is greater than B. So this tells us that we can now order real numbers. We can compare which is bigger and which is smaller. By convention, if A is less than B, then we put A on the left of B. If A is greater than B, then we put A on the right of B. And if A is equal to B, then they represent the same point. So this means A on the left of B is A is less than B. The second case, A is equal to B, so they represent the same point. In the third case, when A is greater than B, then A is on the right of B. Let's now discuss some properties of this inequality. Let A, B, C be real numbers. So first property, transitive property of inequality, or let's call it TPI. So if A is less than B and B is less than C, then A is less than or equal to C. So what we want to show is that A is less than C. How do we show that A is less than C? Following the definition of the order relation less than, this is equivalently saying that C minus A is positive. So that means if we want to show that A is less than C, then we must be able to show that C minus A is positive. Okay, so how do we prove that C minus A is positive? Let's use the given. Since A is less than B and B is less than C, by definition of the order relation less than, it is equivalently saying that B minus A is positive and C minus B is also positive. Again, that's definition of the inequality symbol less than. Now, if B minus A and C minus B are both positive, then by definition of the positive numbers, if we get the sum of two positive numbers, the result must also be positive. That's the definition of positive numbers. But what can we say about this value? That value, actually, that's equal to C minus B plus B minus A, right? That's by commutativity of addition, A1. Give the definition of subtraction, so that's C plus negative B and B plus negative A. Definition of subtraction. Now, regrouping, I can have in the group negative B and B. And then let me rewrite negative A again. So that's associative property of addition, or A2. Looking at the expression inside the bracket, we have C plus 0 plus negative of A because of the existence of additive inverse. And C plus 0 is simply C because 0 is the additive identity. So that's A3. But by definition, again, C plus negative A, definition of subtraction, this is C minus A. That's definition of subtraction. So what we're able to show is that this expression here is positive, but this expression is the same as C minus A. So meaning C minus A is positive. So if C minus A is positive, then the only conclusion is that A is less than C. We are done. Let's look at the second property. Addition property of inequality, and we will call that API. If A is less than B, then A plus C is less than B plus C. That's for any real number C. So meaning, if I add C on both sides of the inequality, I retain the direction of the inequality. So how do you say again that the expression A plus C is less than B plus C? You always follow the definition. Then you must get their difference. And their difference must be positive. So that's how we show that A plus C is less than B plus C. So where are we going to get our expression B plus C minus A plus C? Of course, we're going to use the given A is less than B. So A less than B implies that B minus A is positive. Now, looking at the desired conclusion, again, this is the desired conclusion, but this conclusion here can be rewritten as B plus C minus A minus C. Meaning, eventually, we must have an expression B plus C minus A minus C. But looking at C and negative C, that will just end up to 0. So, we're left with B minus A, which is what we have right now. So, meaning, all we need to do is to express B minus A, including the number C. So, how do we do that? Now, again, we always go back to the definition. B minus A to be written as a sum is B plus the negative of A. So, that's definition of subtraction. But B can be rewritten as B plus 0. Let me just copy negative A. Why? That's the existence of additive identity. So that's A3. Now, 0 can be replaced by a number and its additive inverse. In particular, we want to choose that 0 to be expressed in terms of C. So, in fact, we can write 0 as, so I'm going to write 0 as C plus the additive inverse of C. I can just drop the grouping symbol since addition is associative. So again, we replace 0 by C plus negative C. That's existence of additive inverse. Now, we can regroup B and C. So, I have B plus C. And then, I have the value negative C plus negative A. So that's associativity of addition. But by commutativity, I can interchange the position of negative C and negative A. So I have B plus C plus, instead of negative C plus A, I can write that as negative A plus negative C. Again, this is because of commutativity. Now, finally, I can factor out the additive inverse, and this is also equivalent to copying B plus C and then plus the negative of A plus C. So you can factor out the negative symbol, or that the negative symbol can be distributed over addition. So that's an exercise. Finally, by the definition of subtraction, this will allow us to write the expression as B plus C minus A plus C. So originally, we have the expression B minus A is positive, but we were able to write B minus A as B plus C minus A plus C. So that means this expression here is positive. So if that expression is positive, then we were able to show that indeed A plus C is less than B plus C. Another property of inequality is the multiplication property of inequality, or let's call it MPI. So MPI has two versions. If we have A less than B, then either C is positive or C is negative. Now, if C is positive, then if you multiply C on both sides of the inequality, then the inequality remains the same. So, A times C is less than B times C. So, you have this inequality here. On the other hand, if C is negative and you multiply C both on A and B, then the inequality will be reversed. So, it will become A times C is greater than B times C. And that's the inequality here. Now, I will prove the first case and I will leave the second case as an exercise. Again, exercises are very good technique to reinforce the knowledge learned during discussion. So, we want to show this inequality here. AC is less than BC. As always, if you want to show such inequality, you must show that the difference is positive. So, meaning, BC minus AC must be positive. So this is what we want to show. From the given, we know that A less than B and C greater than 0 implies, or that's equivalently saying, that B minus A is positive from the first inequality and C is also positive from the second inequality. That's the definition of the order relation. But if both B minus A and C are positive, then we can multiply them and the result will still be positive. So this will mean that B minus A times C is still positive. That's the definition of the positive numbers. But let's look at the expression B minus A times C. B minus A times C is actually equal to, by the distributive property, that's BC, B times C, minus A times C. So it's an exercise to show that the distributive property is also applicable when the operation is subtraction. So I will leave that as an exercise. Again, remember, subtraction is defined simply using addition. So now we have the expression that BC minus AC is positive. So that would imply that BC minus AC is positive. But that's what we want to show. We want to show that BC minus AC is positive because that's equivalently saying AC is less than BC. So we are done. Again, the second case, when C is less than 0, will be left as an exercise. Here are some examples of using the inequality property. Show that the natural numbers are positive. So how do we show that a set of numbers, specifically the natural numbers, are positive? Of course, we already know that this set is actually positive, but only because this is what we have been told. We have been told from time immemorial that the set of natural numbers is positive. So now, we will show that it is indeed positive. So we start with the fact that if A is a non-zero real number, by the way, this symbol, if you saw this symbol, the star on a set means you're excluding the additive identity. So this means that this is the set of real number except the element 0. So meaning A is a non-zero number. So if A is a non-zero number, then if you square A, the result is always positive. For example, if I have 2, the squared is 4. So what we're saying is that 4 is positive. If you have negative 2 and you square that, the result is 4. What we're saying is that that number 4 is positive. So again, how do you show that it is indeed positive? So from the given, A is not equal to 0. By trichotomy, we can only have two possible scenarios. Either A is greater than 0 or A is less than 0. That's the trichotomy property. Now, what if A is greater than 0? So, let's look at each cases. If A is greater than 0, then A is positive. Now, if A is positive and you multiply A to itself, then the result must be positive. So, that means A squared, which is A times A, must be positive. So, if A squared is positive, the only logical conclusion is A squared is greater than 0. That's the property of positive numbers. Now, on the other hand, if A is less than 0, then what does that mean? That means negative A is positive. But if negative A is positive and you multiply it to itself, negative A times negative A, and we know from our exercises that negative times negative will be cancelled. So this will just be A times A or A squared. So that means A squared must also be positive because it's the product of two positive numbers. This is positive. This is positive. So A squared is positive means, again, that A squared is greater than 0. So in any case, if A is non-zero, then A squared is greater than 0. Now, knowing that whenever you squared a number, a non-zero number for that matter, the result is always greater than 0, then 1, which is simply 1 squared, must be greater than 0. Simple as that. So, we already know two things. If you have a non-zero number and you square it, it's greater than 0. If you have a number 1, that's also greater than 0. Now, since 1 is greater than 0, right? Then, if we add 1 twice, then 1 plus 1, they are both positive. Then, the only logical conclusion is that 1 plus 1, which is 2, is also positive. Now, 2 is positive and 1 is positive. Then, 2 plus 1 must be positive. But 2 plus 1 is 3. So, 3 is positive. 3 plus 1 is 4. So, 4 is positive. 4 plus 1 is 5. So, 5 is positive. And so on. So, inductively, what we were able to show is that any natural number, since it's a result of the natural number 1 adding it multiple times, it's positive. So, again, to show that any natural number is positive, we will do it by induction. So, by induction, if n is equal to 1, then 1 is positive. We are done. That's from number 2. Okay, so we were able to show that when n is equal to 1, 1 is positive. So we now have the basis for induction. So we can start the hypothesis. We assume n greater than 0 for some natural number n. So we need to show that this is also true for n plus 1. We need to show that n plus 1 is greater than 0. That's what we want to show. But from our previous assumption, the basis of hypothesis, 1 is positive, and because n is greater than 0, n must also be positive. So if 1 and n are both positive, then n plus 1, the sum must also be positive, which will imply that n plus 1 is greater than 0. So we were able to show that for any number n, if n is greater than 0, n plus 1 is also greater than 0. By induction, the hypothesis must be true. And we are done. The next property is usually what we use whenever we want to solve inequality. So, positive and negative products. So, if you have a product, A and B, and it's greater than 0, then you have two possible scenarios. Either both A and B are greater than 0, so A is greater than 0, and B is greater than 0, or the other possibility is that both of them are negative. So either both of them are positive or both of them are negative. Okay? So that's positive product. You can also have a negative product. If A times B is less than 0, then you can only have two possible scenarios. Either A is greater than 0 and B is less than 0, or A is less than 0 and B is greater than 0. So basically, that means that A and B are opposite in signs, or they have different algebraic sign. One is positive and one is negative. So if the product is negative, then each of the factor must have different signs. One is positive and one is negative. But if the product is positive, then both factors have the same sign. Either both of them are positive or both of them are negative. Again, these are the usual technique that we use whenever we want to solve inequality. So let's prove the positive case. When AB is greater than 0, we want to show that either both of them are positive or both of them are negative. Now remember, if you have an assumption that A times B is positive, then you cannot have any of them to be 0. Why? Because if one of them is 0, then the whole product must be 0. Right? That's the multiplication property of 0. If either A is equal to 0 or B is equal to 0, automatic AB will be 0. But our assumption is that AB is positive. So meaning, this cannot happen. Right? So this is a contradiction. So a contradiction means our assumption cannot happen. So anong ibig sabihin? Ibig sabihin, A cannot be 0. Can B be equal to 0? Hindi din. Kasi if B is equal to 0, AB will become 0. So B cannot be 0 as well. So we have both A and B are not 0. By trichotomy, we can only have two possible cases for each of them. Right? So by trichotomy, either A is greater than 0 or A is less than 0. So if A is greater than 0, then that would imply that the multiplicative inverse 1 over A must also be 0. But if 1 over A and A are both 0, then B, which can be written as 1 times B, but 1 can be written as 1 over A times A, and then times B. But again, we can regroup A and B, so I have 1 over A A, B. So, B can be written as 1 over A times B. But if 1 over A is positive, and AB by assumption is positive, AB is positive, then the product must be positive. So, that means B is also positive. So, if A is positive, then we can also conclude that B is positive. So, we have this scenario. Both of them are positive. But what if A is negative? So, on the other hand, if A is negative, then that means 1 over A must also be negative. Again, we can write B as 1 over A times the quantity AB. So, A is negative. AB is positive. So, we have a negative number and a positive number. So, if you multiply them, the product is negative. So, we're able to show that if A is negative, then the product is negative as well. So, we are done. So, I will no longer show you the proof of the second case, and I will leave this as an exercise. So, how do you use negative products or positive products when you are solving inequality? Say we want to solve the inequality 2x plus 3 is less than or equal to 7. So, I will show you step by step, and you just have to supply the reason of validity for each step. Now, we want to have an expression involving only x on the left-hand side and less than or equal to whatever on the right-hand side. So, our goal is to eliminate anything on the left-hand side except x. Okay. So, if we want to eliminate 3, we can do so by adding on the expression 2x plus 3 the additive inverse of 3. So, we can rewrite this as the quantity 2x plus 3 plus the additive inverse of negative 3. But by the property of inequality, this will remain less than or equal to if whatever we add on the left-hand side, we also add on the right-hand side. So, again, supply the reason of validity. Now, by associative property, we can regroup this as 2x plus the quantity 3 plus negative 3. We can simplify by arithmetic 7 plus negative 3 to be 4. Again, what's the reason for validity? Why were we able to regroup 3 and negative 3? But by regrouping 3 and negative 3, we can see that this is equivalent to the statement 2x plus 0 is less than, we're just copying 4. What's the reason? Why were we able to replace 3 plus negative 3 with 0? Now, 2x plus 0 is simply 2x because, again, supply the reason for validity. From this expression, we can multiply 1/2 both sides. So, this can be written as 1/2 times the quantity 2x is less than or equal to 1/2 times 4. So, we were able to multiply a number 1/2 on each side of the inequality. Why can we do that? What's the reason for validity? In the same manner as with the addition, we can regroup 1/2 and 2. And we can simplify 1/2 times 4 to be 2. So, why can we do that? Why can we regroup 1/2 and 2? What's the reason of validity? Now, 1/2, we know, is the multiplicative inverse of 2. So, if we multiply 1/2 and 2, what should be the result? Of course, it should be 1. So, 1 times x is less than or equal to 2. What's the reason? Why were you able to write 1/2 times 2 as 1? Now, 1 times x is simply x. So we have x is less than or equal to 2. So we were able to solve the inequality 2x plus 3 is less than or equal to 7 whenever x is less than or equal to 2. What's the reason? So therefore, our solution set is the set, so let me write it here, all x in the set of rational numbers such that x is less than or equal to 2. That's our solution set. Let's have another example. X squared plus x is greater than 6. Again, rewriting this time, since we have a quadratic expression, we can no longer remove this quadratic expression. But what we can do is we can utilize factoring of quadratic expression. So, we will have to remove 6 on one side and make it 0. So, how will you make 6 0? So, you can add on the right hand side the negative of 6. Of course, whatever you add on the right hand side, you must add as well on the left hand side. Again, supply the validity of reason. Again, supply the reason of validity. What property did we use? So that this inequality, by adding the same number, remain to be greater than. So, what's that property? Now, by our knowledge in algebra, we know that x squared plus x minus 6 is the same as the expression factoring x squared plus x minus 6. That's the same as x plus 3 times x minus 2. It's greater than 6 plus negative is 0. So again, that's just factoring in algebra. Now, we have the product. Product x plus 3 and x minus 2 is positive. So we have by positive product, this is either x plus 3 is greater than 0 and x minus 2 is greater than 0. So that's the first scenario. Or the second scenario is both of them are negative. So either both of them is positive or both of them is negative. So what's the reason of validity? Now, for each scenario, I'm going to get this scenario here and this scenario here. So if x plus 3 is greater than 0, we can easily show that this is equivalent to the expression x is greater than negative 3. So again, you need to do that step by step. You add negative 3. So that 3 and negative 3 becomes 0. And whatever you add on the left hand side, you add on the right hand side. And x minus 2 greater than 0 is equivalent to x greater than 2. So that's the first scenario. Or the second scenario, x plus 3 is less than 0 is equivalent to x is less than negative 3. And x minus 2 less than 0 is equivalent to x less than 2. For this, we use transposition. Now, what do you mean by x greater than negative 3 and x greater than 2? We can imagine x negative 3 and x equals 2 to be two numbers on the number line. So, this is negative 3 and this is 2. So, what does it mean? That it is both true that x is greater than negative 3 and x is greater than 2. Both of them must be true because of the statement and. So, you get the intersection. So, the first expression means x is greater than 2. Or, the second scenario is you have x is less than negative 3. So, anything less than negative 3 and anything less than 2. Both of them must be true. So, you have the case x is less than negative 3. So, you have your solution. The solution set is the set of all real number such that x is greater than 2 union the set of all real number such that x is less than negative 3. Of course, we know that OR means union. Again, I'm leaving as an exercise the shortcut that we used a while ago, the transposition. What does that mean? If I have A plus B less than C, then I can transpose B on the other side. So that's equal to A is less than C minus B. Similarly, for multiplication, if B is not equal to 0 and we have AB is less than C, then I can divide everything by B. So I have C over B. So I'm leaving it again as an exercise to show that these two properties are true.